Okay, folks, we're going to get started here. We're actually starting to talk about kinetics now. And so note that a little recap on kinetics. Whenever we're talking about kinetics, we have the rate. Those are always going to be defined whenever we're doing rate laws, which is these expressions we're looking at, as the rate constant, which are these k values here, equals times the different concentrations that would be involved in speeding the reactions up, but always in terms of reactants, never in terms of products. Okay? Now, if we have something like this right here is first order because it doesn't have a number up there, right? That'd be to the 1 power. Okay? If it has a number here, that would be to the 1 power as well, wouldn't it? So it is first order with respect to the nucleophile, first order with respect to the ligand. Overall, this reaction would be what's called second order. Notice is an SN2 rate, and so it's a rate for a second order reaction. That's what the 2 stands for, isn't it? Okay? And so an SN1 rate, well, it will have the rate constant again, but it's only going to have one concentration there, right? Because an SN1 is a, 1 means first order reaction, right? The other concentration of anything else doesn't matter. Okay? Okay. So, this right here, we have second order. It's going to involve 2 things coming together to do this reaction, right? That's that one-step mechanism. This one right here only has the one thing that the reaction depends on. And that's because we have to have that carbocation form first, right? And that's the slow step. That's the rate determining step. Okay? Okay, so again, these are the SN2 rate, SN1 rate, E2 rate, E1 rate. Again, these are the rate laws. Notice that they directly correlate with those energy diagrams. So the free energy diagram. Recognize right here we have the reactant. That's that step right before our largest barrier, right? Our largest energy barrier. And so that's what causes that to have molecularity of 1. Okay? Over here, on the other hand, your largest energy barrier is when 2 things come together, right? And so this is what gives it a molecularity of 2. It requires 2 things to come together. That's the thing that's slow. Okay? If one thing has to happen, like a heterolytic cleavage, and that's the slow step, that'd be your SN1E1s, right? Okay. No, they're all the slow steps. These are always the slow steps that make the rate. Let me ask you this question. Like, let's say it takes somebody 30 minutes to drive into work. Do they say, it takes me 30 seconds to open my door? Is that included in the calculation? No. You only ever include the slow step in a rate. Okay? And so all of these right here are the slow steps for their corresponding reaction. Okay. In the case of an SN2, that's the only step. There is another step, but all right. So these right here are going to be the rates of your SN1 and SN2 reactions. Notice they're going to depend on the concentration of your main reactant here, that ligand, right? But in an SN2, we also have the nucleophile concentration that matters. Okay? So in the case of an SN2 reaction, your concentration of your ligand and the concentration of your nucleophile both matter. Yes. Overall, it'll be second order if the exponent is 1 for both of these. Okay? There's 2 different things you can say for order. So order is order with respect to the nucleophile is an order of 1. Order with respect to the reaction is a second order reaction because these add up to 2. So there's different terminology. This is 1 step, yeah. So this step is always going to be a second order reaction. It's second order because the slow step is second order. Yeah, this is the only step in this case. I'm just not going to tell you something that's not true in all cases with rate laws. But yes, in this case right here, it's a one-step reaction, so you only have one step, and so the molecularity is that step. For this one, this is a multi-step reaction, and so the molecularity here is the slow step. Anything else just doesn't affect the rate. So let's say we talked about the nucleophile here, which exactly. If you change your nucleophile concentration for the SN1 reactions, doesn't affect the rate. Yeah. It's like if it takes you 50% longer to like look over here, that doesn't change anything. There's only 1 second. Okay. Again, notice that the reactants, that the concentration of the reactant that actually changes your rate is very different for these two things. Okay. So for an SN1 reaction, it's only the ligand that matters. The amount of nucleophile doesn't matter. Okay. So how strong, how good your nucleophile is, how energetically favorable, none of that stuff really matters. Right? For an SN2 reaction, they both matter. So you need both things to come together. You need a good attacker in these cases, okay? Because your attacker's concentration matters. I'm going to use, this has nothing to do with our previous conversation. I usually use this example because it's super memorable for people. But it's kind of a terrible example to use, if I'm being honest, but it's super memorable. Okay, so shooter comes in, door. Okay? We have one shooter, lots of targets here. We're going to have a very fast rate of death, aren't we? Okay? Okay. If we have 5 shooters, same number of targets, we're going to have an even faster rate of death, aren't we? Okay? Exactly. Yep. And it matters for both, right? Because we have the attackers, we have the people getting shot. Okay? We could also call it stabbings if we want. Okay. So what would happen, though, if we don't have attackers? If our attackers are no good? Our attackers couldn't get guns, okay? And so the majority of shooting deaths in the United States are self-deletions, okay? And so... they are. So that is the majority of the shooting deaths in the United States of America. In that case, the rate of your attacker getting to you does not matter, does it? We don't care. It's not going to make that happen any faster, is it? Nope. And so, in fact, it may have nothing to do with it at all. Okay? So, that would be SN1. All that matters is how quickly you can get that to happen. How many people you start with, essentially. I know, it's an incredibly unfortunate way of doing it, but it is so effective. You will probably never forget this moment. I really should try to come up with something that's less just horrific. But every time I try to do something that's less horrific, everybody forgets it. So, what do I do, right? No, nobody remembers it. Everybody ignores it. It is true. Yes, that would work. It is also so much more forgettable. True. So E1 and E2 reactions, again, these are going to differ by their rate laws. The E1, notice E1 looks essentially like the SN1 because the slow step for an E1 and SN1 reaction are the same. Okay? They're the exact same step. Your ligand loses the leaving group, right? And thus it forms the carbocation. Okay? And so your E1 and SN1 reactions have the same sort of rate law here. Your E2 reaction, on the other hand, is going to have the base attacking the hydrogen, and so you'll have a second order reaction again. That's where the 2 comes from. And that gives you your rate law for E2. So let's go ahead and again look at the rate determining steps of a mechanism. You'll notice this is actually a recap from all the previous classes you've had that went over rates before. Now, again, the rate determining step is always the slow step of a reaction. I like to try to use the car example. People usually forget it though, and that's why I've went to shooter example. One year I'll try again to not do the shooter example. But I tell you what, the effectiveness of this lecture has went up tremendously with the shooter example. Maybe I could use plowing into crowds example next. God. Yeah, exactly. If you walk out into the traffic. Okay, so it's just getting worse. Now, again, this is that same example where I was talking about, like if you were taking 30 minutes to drive to work, right? You don't really care about the 10 seconds it takes you to change the lane here. You don't really care about the 10 seconds it takes you to lower your garage door, open the garage door, whatever, right? What you care about is that 30-minute drive portion. The other ones are just so small, they don't really affect the overall rate. Okay. And so this is going to be when species appear in the reactant as the rate determining step of a mechanism. Then your overall reaction rate is going to depend on the concentration of that species. Keep in mind, though, that rate laws are always in terms of reactants. Okay? This can cause a little bit of confusion and issues, right? So this right here is, again, the rate determining step of an SN2 reaction. So we have our nucleophile attacking, okay? And then our leaving group leaves once our nucleophile attacks. And so this happens all in one step. This is the slow step because it has the very large energy barrier you have to overcome. Okay? And again, that right there is the rate law. No, I could ask things about energy barrier without the graph. You would have to determine over, like, if it forms a carbocation, that's going to be very high energy, right? And so that would be a very large energy barrier. It's the same rules as cardinal. So cardinal actually was a measure of the energy differences between different states. You would have to get more specific on the question, though. Like, I don't have to give you energy barriers for every question on this, but some questions I do have to give you barriers, of course. So this is the rate determining step for an SN1. Notice an SN1 is a two-step reaction. And so you have two steps here. You have where the leaving group leaves, and this is going to have an atom that's going to split the charge. Notice you have a positive and negative, right? So if you remember your cardinal rules, this is very high energy, right? See that? This next step actually goes back down energy, doesn't it? And so this is going to be a very fast step because you don't have to overcome a large energy barrier to get it to happen. Okay? Another way of thinking about these speeds are kind of like an entry fee, right? So you're paying an entry fee, and your entry fee happens to be the temperature, the energy around you. Okay? And so if you have a very large entry fee, it's going to take you a lot of time working to build it up, right? To get enough money. Okay? If you have a very small entry fee, you can, work maybe 30 minutes, go to the park, right? And so the slow steps also can be considered entry fees. Larger the entry fee, the harder it is to go through. Okay? That entry fee is directly correspondent to the cardinal rules. Now, this right here is your energy diagram. So this is your free energy diagram. Right here you have your reactants. This is that large energy barrier we were talking about before, right? So we're going from something low energy to something high energy. The energy barrier between them is very large. And so this step right here is our slow step. For step 1, on an SN1 reaction. Now, the second step, even though it's very high energy here, well, it's just a small jump up, right? And so that's very easy to obtain. It's kind of like once you're in the park, it's very easy to pay for the bottle of water in comparison, right? Still expense, but compared to the parks, $300 to get. I think that's what Disneyland is right now, right? Okay. So this right here would be your products. And again, that's step 2, energy very, very small. And so you can overcome that very easily. Okay. All right. Now, this is the comparison between the E1 and E2 rate loss. And so right here we have an E2. See the two things coming together. All happens in one step. This is the large energy barrier then, right? And so it requires a bimolecular mechanism, which is a second order rate law. Okay. This right here is the E1 mechanism. And again, it happens with the same slow step as the SN1, which is it forms the carbocation first. Okay. That takes a lot of energy. It's going to be very slow. And so the slow step is what determines your rate law right here. Okay. All right, so molecularity. The molecularity of a multi-step mechanism is going to be the number of reactant species in that rate determining step. That's actually what ends up giving you your orders. Though for these, it's so far been very easy because it's the first step. And so your reactants end up giving you molecularity. You may remember from back in general chemistry, sometimes it's a little more complicated. You had to substitute things in to get it. Because if it's an intermediate that ends up being in the molecularity, then you have to substitute in reactants to get that. Okay, so it can get a little more complicated if you have like second, third steps that are your slow steps. But not a concern yet. We have not ran into something like that yet. So in SN2 and E2 reactions, these are going to be bimolecular because there's going to be 2 reactant species in each reaction's rate determining step. And so your substrate in either the nucleophile or base in those 2 reactions. Now the SN1 and E1 reactions are going to be unimolecular. They're going to only have 1 species that the rate law depends on. And that's because you only have 1 species on your rate determining step. So you don't have to have something else for the reaction to go forwards, right? Okay, so the quantitative relationship between the reaction rates and the free energies of activation is a result of the transition state theory. This right here being the transition state theory in a calculation with an equation. K is going to be your elementary step rate constant right here. This is going to be equal to a constant, which is C, and then it's T is the absolute temperature in Kelvin. Note, by the way, anytime you have these temperatures like this, where it's just multiplying something, you don't have differences, they're always the absolute temperature. Okay? And then delta G, naught, plus, this is your standard Gibbs free energy of activation. That's that energy barrier, that activation state. R is going to then be the universal gas constant, but keep in mind if you're looking up R values that this one's going to be the one in energy in moles. Okay, so it's going to be joules per mole number. It's not the one that's the Kelvin everything else up here. You gotta be careful about this because it's energies here, right? Okay. So you need to not do the one that is has pressure. Okay. So this one right here, these are going to be your K's for your elementary steps. So the rate constant is going to decrease as your delta G naught increases. So the corresponding reaction rate decreases as well. The rate constant is going to increase as your temperature increases. So the reaction rate increases as you increase temperature. You all already know this because, like, if you want to heat up food faster, what do? If you want to cook faster, you increase the temperature, right? Yeah, higher heat. Yeah. And so you already knew that one really, really well. You've probably used it many times in your life. This is, by the way, the graph. This part right here corresponds to this little box down here. Just to zoom in because you can't actually see it down here. It all looks like 0. And so if we look here, we have the energy barrier percentage of the molecules that would surmount that energy barrier. If we're at 0 degrees Celsius, notice less percent surmount a given energy barrier. So for example, if we look up at 5 here, and then we go over, it would be somewhere around there, right? So we have a bit less than 30% of the molecules would be able to surmount that energy barrier. Okay? This happens because when we're looking at a temperature, it's randomized kinetic energy. And so you only have a small portion of the population that's going to be above a certain amount of energy. And you'll have the rest of the population that will be below that energy. Okay? Okay. So let's talk about theoretical rate laws. So theoretical rate law is going to be derived from a proposed mechanism. It's actually one of the ways that you would actually test a mechanism is you would see if your proposed rate law actually follows data, real-world data, for that reaction. So each elementary step is going to have an associated theoretical rate law. For an elementary step, we would have this right here, coefficient, times the reactant species, plus coefficient times the reaction species. And this is going to end up giving you your products on the other side of that. Now, the theoretical rate law for this right here, assuming this is our elementary step right here, and is the slowest step, is going to be rate, again, this is theoretical, equals K, which is the rate constant, times the concentration of A here, which is that reactant species, to the power of A, the coefficient, times the concentration of B reactant species, to the power of B coefficient. Okay. Now, notice again, this only works for elementary steps. If you look at an overall reaction, this does not work. Okay? Overall reactions don't have these theoretical rate laws like this, that you can just take the coefficients. Okay? So you got to be careful about that. This is for an elementary step, one step of the mechanism. Right? What you actually end up taking here for the overall rate law for reaction would be the slow steps. Elementary step, right? The slow step. You would take this rate law for the slow step. Now again, A and B, reactants concentration. The exponents A and B actually represent the orders. If we're talking about with respect to A, the order would be this small a here. B, the order would be this small b here. The overall order would be those two things added together. By the way, I've talked about unimolecular, bimolecular. You notice I haven't talked about trimolecular. Is trimolecular really a thing? It hasn't actually been observed and then verified. So it has yet to actually be verified that has ever been observed. Now, can you have a third order reaction? Yes. Yes. And typically that means you have like multiple steps that are fairly slow. And so they can compound a little bit. Okay? They have to be pretty similar in speed though. You can also have a trimolecular reaction is theoretically possible, but the problem being that like two things coming together and hitting each other are pretty rare, right? When it's just random. And three things all coming together to hit each other at the same time is incredibly unlikely. Okay? And so trimolecular is actually very unlikely to happen. It'd be very slow if it does happen. But theoretically, yeah, it probably does exist. Are you likely to actually ever accomplish a reaction with it? Probably not. Though you could have like make a catalyst or something that might be able to bring it up. And they can contrive conditions where they think they'll be able to get, and they usually can get something like it. So this may appear from overall reactions that the SN1 and SN2 mechanisms yields the same products. In fact, a lot of the reactions we've talked about so far have at least one of the products for the SN1 that is the same as the SN2. Likewise, you can may appear from the outside that the E2 and E1 reactions yield the same product, and there are no differences there. But the mechanism can be still different, right? The way you got there can still be different. Okay. Like there's 3 different facilities that make this phone here. It still ended up in my pocket, right? So the exact mechanism can give you the same products. The nature of the reaction can yield subtle but important differences in your products. For example, stereochemistry oftentimes is going to be a major consideration. So one of the biggest differences is an SN1 reaction typically has a difference in stereochemistry with an SN2 reaction. Because an SN2 reaction happens on one step, the mechanism actually determines the stereochemistry. Okay? And you'll get a very set stereochemistry every time. There's not going to be a lot of variance between the stereochemistry. There will be no variance in stereochemistry with an SN2 reaction. An SN1 reaction, on the other hand, because you break that bond, you make the carbocation, right? Well, the carbocation is flat. Okay? It is an sp3, it has a free p, an sp2, excuse me, has a free p orbital. It's flat, right? It's trigonal planar typically. And so that means you can attack from either side, like we had shown in the orbital diagrams. And thus you can get either enantiomer, can't you? So the stereochemistry of an E1 reaction is going to differ from that of an E2 reaction, again for the same reasons. The E2 reaction, because it happens all in one step, it always has its final product dictated. Okay? Whatever you start with dictates what you have for your final product. You always get a very, very predictable stereochemistries. Okay? On the other hand, in E1, because you're making a carbocation, well, you have no control over the stereochemistry. It can go from one direction or the other. Okay? You've greatly reduced your control over that stereochemistry. Most things you have no control, but there's a few cases. Now, this is the SN2 reaction, and notice we get exactly one stereoisomer from this. Okay? In an SN2 reaction, you always have attack from the opposite side. In case you're wondering where this stuff's coming from, this is actually IC. That's why we talked about IC in the orbitals and attacking from the opposite side. So we attack from the opposite side. So in this case, coming out towards you for the chloride, right? The iodide would come and attack like this. Okay? And so you're going to end up with the iodine on the exact opposite side you were. Okay? It's going to invert your stereochemistry. And so you went from an S, 1 chloro, to an R, 1 iodo. Again, it gave you exactly one stereoisomer. It is a stereospecific reaction. And so the SN2's reaction is stereospecific. Notice the words actually tell you what that means, right? Stereo, as in stereoisomer, specific. Always gives you the same thing, right? Okay. Now notice that is different than it gives you the same stereochemistry. It does not, right? It gives you a predictable stereochemistry. Okay. Okay. Again, that initial configuration entirely determines the resulting product. Okay. Now, this is the backside attack right here. This is the chloride that was sticking out at you before. And here's the iodine that's attacking from the opposite side. Okay. Remember, it's attacking that little orbital over here, right? And so this is going to act a lot like an inverted umbrella. That's the standard way of describing this, which is known as a Walden inversion, in fact. Again, this is called backside attack. And so you attack from the backside. This is actually the intermediate. That's the high energy state that we were having to overcome, right? And then the chloride leaves. It leaves you with the iodine. And that's going to cause all the rest of the groups to invert the other way, doesn't it? Okay? Just like an umbrella, where you just invert all the other groups on it, except for the main leg. Does anybody have any questions about that? No? Okay. All right, now, Front side attack. This does not occur in an SN2 reaction. So in a front side attack, the three groups would actually remain on the same side of the product. This is actually a few different reasons for this, but steric hindrance is a very large part of this. If you did a front side attack, it would have to come in the same side that you have your leaving group leave, right? The other part of this is charge repulsion. Remember, the chloride is going to have your negative, partial negative charge here, and it's the one that's building up negative charge when you put this on. And so you'd have both your negative charges right next to each other. And that's going to be very, very unstable. Now, there's actually an even bigger reason for this, which is the fact that if we did an attack from here, the orbitals would not actually align with it. Yeah. And so to align with the orbital, put electron density into the orbital here and cause that to leave, it has to attack the orbital right there, right? That opposite phase part of that orbital. Okay. Okay. And so this is actually the front side charge repulsion. We can see the electron density around that chloride here, and see it comes in, it has to get right next to it, right? It's just going to bounce right off. Forget even trying to do the reaction, it's just going to right off there. It can't even get close. Over here, on the other hand, we see that the charge density is very low, isn't it? Because this has the partial positive charge over here. And so it can attack from this side much, much easier, right? It doesn't get rejected by that large charge density on the other side. So let's draw a complete detailed mechanism for the following reaction, assuming that takes place in an SN2 mechanism. Pay attention to the stereochemistry. I'm going to move on pretty quickly because I need to make some time here. Okay, so again, this is going to be a backside attack, right? What is our leaving group? Bromo. And so we're going to attack at the bromo. So the mechanism is going to look like this. This is our nucleophile right here, right? We're attacking with our electron density and a backside attack right here on the opposite side of that bromide. The bromide is going to leave. So when we write this in, notice that we have to take this sulfur, and whatever our leaving group's geometry was, it has to be the opposite of that, doesn't it? Okay? And so instead of being forwards towards you, the sulfur has to go backwards away from you. Because it has to attack from the opposite side. That does mean the hydrogen ends up being inverted. Because it's a Walden inversion, right? Like the umbrella. Okay. Now, our stereochemistry of our SN1 reaction. These are really easy because we lose our leaving group. So we only have three things around us, and that means we have the sp2 arrangement, which is that trigonal planar arrangement, don't we? Okay. And so you're always going to get a mixture of R and S enantiomers. If there's no other forces acting on this, then what you're going to end up with is a racemic mixture. Okay, 50-50. If there's some forces that are going to change the energies of one versus the other, so it has a three-dimensional environment, it has chirality to the environment, then you can get different amounts of these. But again, you're going to get front and backside attacks on that carbocation. Now, the mechanism of our SN1 reaction, again, if you forgot any of it, was the chloride, the leaving group here, is going to leave first. We're going to have our carbocation, and so that's now flat, right? And then the attacking group here, which is our nucleophile, well, now it's free to attack from the top, it's free to attack from the bottom, right? Either side is open, okay? They both have orbitals there. It's an open p orbital on both sides, right? And so front, back, both attacks work, okay? And we get both options. So it's pure probability of is it going to attack from the front, is it going to attack from the back, okay? Backside, front side attacks, pure probability. In this case, it's probably very close to 50-50. Now, again, you're going to produce both configurations, so you're going to have both the R and S configurations that will be produced. If the reactants in the environment are both achiral, you're going to have equal amounts, and so you'll get exactly equal amounts, 50-50. Okay? if you have unequal amounts of the reactants or the environment is chiral, then you're going to get chiral behaviors, and so that means that one will be favored over the other. Okay. By the way, why would unequal amounts cause this, where you get a mixture of the two? If I have an odd number of flips, so if I have unequal amounts of these reactants, where it's a not even number that's going to come out of this, I'll end up with one more than the other, right? So what ends up happening is if I have unequal amounts, I'll end up with a little bit more of the other, just through the pure fact of the probabilities that I have to end up with an uneven number, right? So the ion pair in an SN1 reaction. This right here is your ion pair that's formed. Again, it's going to be the leaving group leaves. That will form your negative ion typically. The other one is going to be the carbocation. This is going to form your positively charged ion. So again, your nucleophile is going to prefer being attacked if it's an ion pair from the side that the ligand did not leave from. But this is only if it forms an ion pair. So again, you know how you have like ammonium chloride as a salt? That'd be an ion pair, right? They're attracted to each other. Okay. Keep in mind that a lot of situations, this is not going to happen. You don't have to deal with this. Okay. But this is going to be that electrostatic attraction keeps the leaving group from actually associating and leaving the carbocation. They're going to be attracted, so they stay somewhat near each other. Okay. Now, again, the nucleophile can still attack from both sides. This is going to be a longer distance attraction. You'll have more space here for it to attack. So it is possible to get the other side attack. But it's going to prefer not going near the negative charge, right? And so you're going to get less of that. Okay. This is diisomers in an SN1 reaction. So if the reactant right here has two chiral centers, like we see right there, only one is going to be affected by your leaving group. And so this is going to cause diisomers, right? And so the iodide can approach from either side of that carbon still. That's still true. And so the RNS can both be produced, right? But they're not going to be equally likely. Okay? And that's because one side has this hydroxide here. One side has the OH, right? The hydroxy group. Exactly. One side's going to have a little more negative charge over there, and that's going to repel some of the cases where the iodide tries to come in, right? Okay. And so some of these cases where the iodide's trying to approach from this hydroxide side, from the oxygen side, will end up being repelled, thus giving you an unequal split. Right. And again, that's that chiral molecule here. We could also have a chiral environment that would change things. Okay. Now, this again is going to be diisomers formed in unequal amounts. So notice again, we have this approach here from this side. It's going to interact with that oxygen, isn't it? Not all of the cases where it approaches from that side, but enough that you'll get an uneven split. All right. So let's look at this case right here. If you draw the complete detailed mechanism for this reaction, we'll assume that this takes place by an SN1 mechanism. Will the reaction produce a single stereoisomer, or will it produce a mixture of stereoisomers? If a mixture, are they going to be equal amounts? Okay, if it's an SN1, is it going to be a mixture or just one? Mixture. Do you think they're going to be equal amounts? No, we have that oxygen again, right? So we have a chiral environment. We have a chiral molecule here we're doing the reaction on. Chiral environment would be using things like a enzyme would be an example of a chiral environment. It would list that. under reaction conditions? It would indicate like we're using an enzyme right here, something like that. So this right here is going to be your bromide. You leave, you produce your not a chiral center, choose the carbocation. Then you're going to attack from either direction, and so that would give you your two options, right? Now, because this right here is chiral right there as well, this is going to be produced in unequal amounts. And so you'll have your diisomers, but they're not going to be equal amounts. So this is the stereochemistry of an E2 reaction again. And notice that E2 reactions are going to favor the substrate formation in which the leaving group and the hydrogen atom are eliminated. They're anti to each other. So you would expect these to be on opposite sides, like this right here. So the hydrogen and the leaving group want to be on opposite sides. If you remember the orbitals we had talked about, those orbitals that we had talked about, you can get the reaction happening where they're not anti, but it is much less energetically favorable than being anti to each other. Okay? And so this one is less of a hard, just is this way rule. Okay? Now, the conformation in which the H and the leaving group are anti to each other, this is called anti-coplanar or anti-paraplanar. So this right here is a Newman projection of this, and you can see that they're anti right here. Okay. If we were to rotate these, you would see that these would be the gauche forms right there. This is the anti right here. Both. Oh, what was the... Okay. 1 second. Okay, I'm sorry. What was the question? I was... Oh, Jesus. Apparently. Okay. So the anti-coplanar is going to be where they're on the same plane. Anti-paraplanar as in different plane. So this right here is going to be the anti-coplanar conformation. And what you can see here is right here, where they're on the same plane, but they're anti. See that? We have one plane that goes through them, and they're anti on that plane. Okay. So, did I cover? All right, now. I didn't put a figure, did I? Okay. Could you remind me? I'll send out a little figure and talk about it. Because I also don't have a model to make it up here. Yeah. So this right here is your attractions from opposite sides. So one of the reasons why this is preferred for the anti-coplanar orientation of your substrate is that you have the negative charge from the leaving group. So if you try to attack from the same side as the negative charge from the leaving group, it's going to be repelled in many of those cases. If you try to attack from the opposite side, keep in mind that the hydrogens are typically the positive sides of it, right? So you're going to be coming in on the positive side of this. Okay. One of the largest differences, though, is the orbitals that we had talked about in the previous lessons. And that is that the orbitals actually overlap for your electrons to flow into the bonds. Okay. Okay. Did I really not put that? All right. So this is your E2 right here, where you're getting a mixture of diisomers. So the E2 can produce the mixture of an E and Z diisomers. The diisomer that is favored is going to be the one that's produced from your most stable anti-coplanar, which is the hydrogen that's leaving and the bromide being on opposite sides. Okay, so in this case right here, we can get a mixture of diisomers, but we may have a major product. Major product is the one we make the most of. And we have a minor product. Minor is the one we make less of. Okay? And so this one is going to be your major product that we make more of right here. Now, notice that in this case, we can actually have two coplanar options because we have two hydrogens. Okay? And so if you have two coplanar options, which option is going to be the one that's favored? Well, the lower energy, right? The more stable one. And so when we look at E versus Z, right? What did we discuss for those configurations? Well, E was lower energy and more stable, wasn't it? Z was higher energy. Okay. So when you have two options that are both coplanar, the way you determine which is going to be your major and minor product is going to be which one is the more stable one. Okay. And it's favored to have the larger groups further away from each other. So that's that same steric hindrance. Okay. So right here, I have some diisomers forming for the E2. Yeah, this is my actual Newman projections for the ones we were looking at. And so here I have my hydrogen 1 option, opposite of bromine. And that's that coplanar right there. And this one is anti-coplanar. And this one is the anti-coplanar for the second hydrogen option right there. Okay, they can both take on anti-coplanar conformations to do the reaction. Now, the difference between these can both be made. The difference is that this one is E, right? And so it is lower overall energy, less steric hindrance here than this one, because these are on the same side. Okay, this is an E1 reaction. It's going to produce a mixture of the E and Z configurations around the double bond that are formed in our products. Again, we're going to go through that carbocation intermediate. And so there is, however, a major and minor product depending on the size of the groups attached. Okay? And again, that EZ isomers are going to give you that. Okay? So this case right here, we have the E, and that puts these large, higher priority groups on opposite sides of the double bond, right? And so this is going to be lower energy. This one right here is your minor product. And that's going to be where you have the large groups on the same side, because that's going to give you a lot more steric hindrance, right? Keep in mind that this actually interacts with the energy barriers too. Okay? So for example, when you have the carbocation here, these being on the same side, they can rotate off that. So you don't have the double bond yet, right? Okay, so this is what it looks like when we're looking at that reaction mechanism. So remember, we're going to lose the bromide. We'll make the carbocation, right? And so it has free rotation around that single bond in between. Okay? And so when you go to attack this hydrogen over here and take that off to make the double bond, again, it's not going to have an not really anything, right? If we're in this form right here, this carbocation is actually less likely to be made in the first place, isn't it? Because these are just conformers of each other. They have free rotation. Okay? And so this one here is just less likely to be there when you're attacking in the first place. This one here is more likely to be there in the first place. You're going to have a larger population of that. Okay? And so this is actually the major determinant for this of which conformation you're going to get, which isomer you're going to get. Is just this steric strain in this step right here. Again, this would be your major product. That's the E. Large groups on the opposite side. Z is your minor product. Okay, so let's talk about the reasonableness of a mechanism, and then proton transfers and carbocation rearrangements. One of the things we need to keep in mind here is that all the things I've been building up to this point, these are all the steps you need to understand to do this, right? That's why we were doing that awkward, this is this step. It felt weird, it felt wrong, but this is why. So the examples of your SN1, SN2, E1, and E2 mechanisms, these have been our simplest examples. We didn't have to do anything to set them up. We didn't have to do anything to finish them off. It's just pure E1, E2, nothing else to consider. So many of these are going to have additional elementary steps either before or after these reactions. Okay, they're not going to just be the E1, E2 elementary steps. This is going to make our mechanisms longer and more complex, but it also gives us those layers of complexity, gives us the ability to make things, right? If you could only do these very limited things, you would have nothing that you could make. Okay? It would be like only being able to color a book in yellow and pink. Be very limiting, right? So two of the most common additional steps are going to be your proton transfer steps, extremely common, especially in biology. The carbocation rearrangements are going to be extremely common as well, especially in organic chemistry. Now, the reasonableness is going to be very important. So when you're incorporating these steps, you need to do them in a reasonable way that actually makes sense with all the other chemistry you know. Okay? Now, strong acids generally should not appear in a mechanism under basic conditions. If you're doing this reaction in NaOH, it doesn't make any sense to make hydronium. No, that's, it's silly, right? But know that you're going to be like tempted, because the shortest way would be to make hydronium, and you're going to be tempted, and you're going to try to do it, and you need to go, wait a second, I'm basic conditions. No. No, that doesn't make sense. Strong bases also should not appear in a mechanism under acidic conditions. If you're under acidic conditions, you're not going to make OH minus, right? You're not going to make these strong bases like an amide that's negative, right? That doesn't make any sense. Those would have to react to the proton immediately, right? So them existing for any period of time is very unlikely. Proton transfer steps are very fast steps. Of these steps you could have, they're some of the fastest steps you can do. This is purely because protons are so light. Okay? And so protons actually can get transmitted incredibly fast. Right? Now, they should be incorporated before and after other elementary steps. This will help you, number one, avoid incompatible species. But number two, like if you have two molecules coming together, they're going to take a lot longer to do than a proton transfer. Okay? So if you're trying to move a chloride or a carbon, that's going to take a lot more energy. It's going to be a lot slower, right? Versus moving a proton. So strong acids will be roughly stronger than H3O+. Weak acids are going to be significantly weaker than H3O+. That's the definition of a cutoff for strong and weak acids. The strong bases are going to be stronger than OH-. Weak bases, significantly weaker than OH-. That's the cutoff for bases as well. Okay. Any acid whose pK is less than 0, this is going to be a strong acid. So if the pK is less than 0, you should expect it to be act as a strong acid. Any base whose conjugate acid has a pK of greater than 14, this is considered a strong base. And so these are some typical examples of strong acids, weak acids, strong bases, and weak bases right here. Okay. Notice that chloride, bromide, and iodide are all weak bases. They're just incredibly weak bases. Okay. They're the conjugates of strong acids, in case you're wondering. These would be basic conditions right here. See the KOH right there? That tells you basic conditions, doesn't it? Yeah, that's a strong base. Okay. And so this is going to be highly basic conditions right here. And that's your reaction. So this right here would actually be a proposed mechanism. And let's kind of consider the reasonableness or unreasonableness of this. Okay. So right here, what we have is we have an oxygen coming in. It's going to attack this. Our leaving group then leaves. And this leaves you with a protonated species right here. And that's an acidic species, isn't it? And so forming an acidic species in basic conditions, that doesn't make sense, does it? Yeah. So that wasn't reasonable. Okay. So what we should do is we should move the proton transfer step 2 in front of it. Right? So the first step is going to be a strong base, deprotonates our alcohol. Right? And this is going to give us the alkoxide, right? That's then going to attack. That's the one that's going to act as a nucleophile. It's a stronger nucleophile anyways, right? And so then we'll leave bromine, and that gives us our product. And so that's a reasonable one. We don't have any strong acids up here. We have bases, but we're in basic environment, aren't we? So that makes a lot of sense. You good? Okay. All right, so this is acidic conditions. Okay, so here we have an acid that's giving us acidic conditions. This sulfuric acid, very common use for this, in fact, is a very strong acid. Funny enough, one of our reactants is also a strong acid. So this is a very acidic environment. It's actually a very dangerous environment, if you want to know the truth. Now, this right here would be the heterolysis, and we'd form a carbocation, right? And then we'd form hydroxide. What's wrong with that? It's basic. I formed a base in an acidic environment, didn't I? No. This is another opportunity, by the way, that don't do it too loud because you guys probably are studying somewhere that needs to be somewhat quiet. But base. Acid. No. Okay. So again, can't form a base in an acidic environment, so we move that proton step up before it, right? And so we have our acidic environment. We're going to protonate that OH. That's going to give us an acidic form, right? H2O+. So this right here is an acid. And yeah, this is a base, but it's an incredibly weak base, right? It's a conjugate base for a strong acid. Okay? And that makes a lot of sense because we're in an acidic environment. We're making an acid, right? That makes sense. And so then that's going to leave as water. Notice that leaves as water. It's a great leaving group. Forms the carbocation. And now we're going to attack with the bromine. By the way, one of the things I want to point out here for a second, okay, is that these first ones didn't really make a lot of sense in the first place. Like you have OH attacking here. This is not a good nucleophile. It's not a strong one. Attacking this. This is a good leaving group. But this doesn't really make any sense. Like this is way less energy than this, right? This, on the other hand, we already had something super high energy. It made something higher energy that then did an attack, right? And so that made a lot more sense if we actually start thinking about all the layers to it, right? So I know that I've given you a simple rule to follow, but it will self-reinforce. If you actually pay attention to what's going on and follow the cardinal rules, it self-reinforces. Everything before was still true, okay? It's not like I've changed the rules. I've just given you a simpler way to look at the rules, okay? Again, this same thing, right? Not a good leaving group. This is less stable over here than it is over here by a lot, right? And so this one, on the other hand, well, this is high energy in the first place. Protonates it. That's high energy now. So coming apart as the carbocation makes a lot of sense. Okay, so drawing a mechanism for the elimination reaction shown here, assuming it takes place via an E1 mechanism. Okay, so what sort of environment am I looking at? Acidic environment, aren't I? Very good. And so these are the other conditions, obviously, water. And they're actually going to help us finish the reaction. Okay, and so I'm going to do a what sort of step for first one? Okay, that makes a lot of sense. We'll go ahead and talk about the right one first, since you did the right ones. We're all doing really good. But we'll go back to the wrong. Okay, So we protonate first, right? Okay, we're going to protonate the oxygen. It's going to make our strong acid form. Okay, this is now a very good leaving group. So we'll do the heterolysis. That'll give us the carbocation. And then we just need to use our base. In this case, the base is just going to be water because we have that freely available. And that's going to take the H+, leaving us with the electrons to go into a double bond, right? And that gives us the elimination of the H+. Perfect. Notice we needed the water to finish it off for us. Yeah. Technically, you could have also protonated this form here, but it would have been pretty high energy. The water lets us be lower energy and dilute it. In case you're wondering. This right here would be this is wrong, isn't it? Yeah. So if we were to just do the heterolysis right, that'd form the carbocation, then we'd form a base. Oops, we're in a base. We're in an acidic environment. We formed a base. That doesn't make any sense, right? That one's wrong. Okay. This right here is going to be the ethylene oxide or oxirane. So there's going to be intramolecular versus solvent-mediated proton transfer reactions. So in the case of a intramolecular reaction, this is going to be transferring the electron from one spot to the other. Solvent is going to be where you transfer the electron onto a solvent. And it may come back somewhere else, but you're going to transfer it to a solvent. Okay. And so this is oxirane right here reacting with ammonia. This will form this right here. This is the mechanism. So you have the ammonia attacking via an SN2 mechanism. Notice that we form the negative charge over here because this leaves us the leaving group, kind of, right? Still part of the molecule, but left that position. And this one right here is going to be protonated, isn't it? And so what does Cardinal tell you about that? That's less stable than it should be, right? So this one right here wants that hydrogen. This one wants to lose it, doesn't it? So how is that going to happen? Yeah, we probably need to do another step, right? This is going to be very difficult to get to fold back, right? Okay. It's like certain parts where you can't touch your fingers together from certain distances, right? So this is just too small of a chain to actually go around and do the intramolecular reach here. So this can't bend enough to actually get that hydrogen to contact here, can it? Yeah. And so this doesn't make any sense to do an intramolecular within the molecule proton transfer. So you're going to need a solvent to do it. Water or any solvent. Yeah. So some solvent, water in this case, perfect. Transfer the proton to the water. The water can then transfer the proton back, right? Okay. Or vice versa. It really kind of, the only thing that matters here in terms of the order that you'd go is your pKa's. Mm-hmm. Just because this was on this step. So at the very end of the reaction, you would still have H3O plus, OH minus, and then you just don't care about them. They're not the main focus of the reaction. Because you do generate. You generate OH minus, you generate H3O plus for these specific steps. Yeah. For the final product, you would just account this one because these would neutralize each other. Okay. Okay. So again, this right here would be another termolecular step. This would have three reactants coming together all at once, where it would have to have the waters being involved in this reaction at the same time. That obviously can't happen. Carbocation rearrangements are the last one. We'd already talked about them several times, but carbocation rearrangements are going to be where you have the carbocation. It's going to pull the groups next to it over to complete its octet. Okay. Okay, folks. Good luck with the homework. Okay. Did move it back a little bit. Positive. Okay. Anybody have any